A small fish vanished. No chase. No movement. One moment it existed, the next, it was gone. That is not a description of magic. That is a description of *Antennarius striatus*, the striated frogfish, filmed in 2006 by Grobecker Pietsch and colleagues at the University of Washington using a high-speed camera running at 500 frames per second. The strike completed in 6 milliseconds. To understand what that number means, consider your own hand. A nerve impulse traveling from your fingertip to your spinal cord takes 15 milliseconds. The frogfish's strike is over before that signal finishes its journey. The prey is already inside the mouth before the physics of the event could be registered by anything watching. Pietsch published the measurement in 2009 in *Biology, letters *. His finding was precise. The strike of the frogfish is the fastest recorded feeding strike among fishes, completed in as little as 6 ms. Fastest among fishes, faster than eels, faster than moray, faster than any ambush predator in the ocean. But here is what makes the frogfish strange beyond its speed. It achieves this while doing absolutely nothing. It sits on a rubble seafloor, motionless for hours, its skin lumpy and textured and threaded with filaments, reads to every nearby creature as encrusting sponge. Not similar to sponge. Indistinguishable. Its pectoral fins are planted flat against the substrate, like hands pressed to a table. Above its snout, a single modified spine rises. The Elysium, Pietsch and Grobecker described the fleshy tip. The Esca in their 1987 Stanford University Press monograph. It is waved in a manner that closely resembles the movements of small prey organisms. The frogfish does not hunt. It decorates itself as rubble, extends a lure made from its own skeleton, and waits for something to come close enough. By the end of this video, there is a specific ratio. Strike speed measured against the documented escape speed of the frogfish's fastest known prey reveals the 6 millisecond figure is not just record-breaking. It is, by a measurable and documented margin, far beyond anything the frogfish should need. That gap exists in the peer-reviewed literature. It has no consensus explanation. The obvious answer writes itself. Faster strike, more prey caught, more offspring. The trait spreads. Evolution selects for speed. Case closed. Except the numbers don't close the case. They blow it open. Small reef fish, damselfish, juvenile wrasse, the frogfish's documented prey, max out their escape velocity at 20 body lengths per second under optimal conditions. That figure comes from kinematic studies of the sea start reflex, the fastest escape response vertebrates produce. 20 body lengths per second is genuinely fast. It is also nowhere near enough. The frogfish strikes at 82 body lengths per second. That is not a narrow margin. That is a factor of 4. A frogfish striking at 40 body lengths per second, half its documented speed, would still catch every prey item on record. A frogfish striking at 20 body lengths per second would still catch most of them. The prey simply cannot respond in time regardless. Grobecker Pietsch at the University of Washington confirmed the 6 millisecond figure in 2009. Published in Biology Letters, the prey's sea start reflex alone takes 20 milliseconds to initiate. The frogfish is already finished before the prey's own muscles receive the signal to run. So the speed competition model predicts a specific outcome. Evolution pressures the frogfish toward the minimum speed necessary to outrun its prey. Maybe 25 body lengths per second. Maybe 30. What it does not predict is 82. Shrimp are faster than fish over short bursts. Their tail flip escape is explosive. Pietsch's data covered those too. Still not close. The gap held across every documented prey species. The selection pressure explanation requires a target, a ceiling the animal was racing toward. But the prey's ceiling was cleared at a fraction of the frogfish's actual speed. If the prey never required this, if natural selection wasn't chasing a faster fish or a quicker shrimp, then what exactly was it building toward? Here is what the frogfish actually does. Not muscle, not speed in the conventional sense. Preloaded pressure, a hydraulic trap cocked before the prey ever arrives. The opercular valves, the gill covers, seal shut. The hyoid bone drops. In 6 milliseconds, the buccal cavity expands to 12 times its resting volume. The prey does not get eaten. It gets inhaled. The water around it deflects inward like cloth pulled through a drain. Theodore Pietsch at the University of Washington documented this in 2009, publishing the kinematic measurements in Biology Letters. 6 milliseconds. The strike completes before the frogfish's own nervous system has finished processing the decision to strike. Consider that number against a human nerve impulse traveling from fingertip to spinal cord. 20 milliseconds. The prey is already inside the mouth before a signal that fast could complete a single relay. Stephen Day's 2015 hydrodynamic analysis at Virginia Tech calculated the suction forces generated. Prey drawn inward at velocities exceeding 100 body lengths per second. Not pulled. Translated. Physically relocated by differential pressure alone. But here is what the literature cannot close. The strike is 3 to 4 times faster than any documented prey item requires. No prey species the frogfish is known to target can escape a strike even twice as slow. Researchers have a name for this gap: excess performance capacity. In the frogfish, it is the largest measured in any ambush vertebrate. No peer-reviewed consensus explains it. The over-engineering sits in the data, circled unanswered. A small fish vanished at the opening. No chase. No movement. The receipt finally is this: a pressure system so disproportionate to its task that the task itself may not be the point. What the frogfish built is not a trap calibrated to its prey. It is a trap calibrated to something no known prey has yet presented. Science has not determined what that something is. The entry is filed. The number stands. The deep index remains open.